Hi, welcome to the first video of this series about understanding audio measurements. We will start with the basics and look at the signal in time domain and frequency domain and what are decibels. I have here Virtins Multi-Instrument tool, but these are common concepts, so it doesn't matter what software or hardware you use. So we have here time domain, kind of oscilloscope view, and here is a spectrum analyzer, so frequency domain. We have just noise here. I have my DAC and ADC connected as loopback, so when I press a signal on here, I have a tone coming. So here we see the signal in time domain, and here we see it in frequency domain. I won't be going into mathematical or very technical details. I try to focus on the practical point of what these concepts mean. Let's look at the time domain first. So let's just hide the spectrum analyzer for now. So what can we tell about this signal? So we see it's symmetrical around 0. So its mean value is around 0 volts. It's a microvolts. And then the peak value is around plus minus 5 volts. We can also see here max and min. And the RMS value is around 3.6 volts. We can also see it here. And that's the RMS value is square root of 2 of the peak value. So since all software and almost all hardware these days are digital devices don't know anything about volts. The only thing hardware and software can deal with in terms of digital signals is something referenced to their full-scale level, the full-scale level of the ADC or DAC of the device. And this full scale is abbreviated by FS. And here we have now the output as dBFS and the signal coming in as dBFS. So this is DAC's full scale and this is ADC's full scale. And they're the same now because they're both operating at the same level of 4 volts RMS. I have told the software that the reference is 4 volts RMS, so it knows that when the ADC is getting signal which is 1 dB below its full scale level, it corresponds to 3.6 volts. So this dBFS is one quite important dB unit which is related to converters like ADCs and DACs, because that's the only world the converters live in. They only know what's the signal level compared to their own internal reference level. And that's one of the main things of dB. dB is always a ratio. It is something compared to another reference signal. When we talk about THD in future videos, that's what's the distortion level compared to the fundamental signal. dBFS here is a digital unit, the signal level compared to the full-scale reference. Then we have dBV, which is the signal level compared to 1 volt signal. dBm, which is a unit of power, commonly used in RF engineering. That's the signal level reference to 1 milliwatt of power. And probably how most of the people know about dBs is when they talk about sound pressure level, how loud something is. And that's also a ratio. It's just a sound level compared to this agreed reference level, which somehow corresponds to the threshold of human hearing. At this point, it may not be obvious yet why do we use dBs instead of just using percentage or absolute level, but the benefit comes when we start dealing with very small or very large numbers. For example, a factor of 100, 1%, it's 40 dB, but then 1000 is 60 dB, 10,000 is 80 dB, and 1 million is 120 dB. So for example, plus minus 120 dB, we can cover a huge range. Okay, let's make the time view just small now and let's focus on the spectrum analyzer view. This is the FFT Fourier transform of the signal above. I won't go to the math behind Fourier theorem, but just focus on the practical aspects. So here we have the frequency domain representation of this same signal here. So what does this FFT tell us about the signal? So we have this one peak here, what we call the fundamental, that's around 1 kilohertz. Tells here that it's 997 hertz, and that's what we put out of the DAC. Then we have noise, and we have some harmonics, which means that they are multiples of the 1 kilohertz. So there's 2, 3, 4, 5, and there's something else happening here as well. I don't know what is this. And if we look at the scale here, this again, it's dBFS. So the fundamental is quite close to 0 dBFS. And we can see that the highest harmonic, the fifth harmonic here, is almost 120 dB down, because this is not quite 0 from the fundamental. The software does some calculations for us here. So THD, it's around minus 115. So what it does, it compares this fundamental peak to all these counted together, the harmonics. So the minus means that the sum of the harmonics is this much down from the fundamental. And here we get one good example why we like to use decibels. So here's the same distortion number in percentage and in dB. And when you start talking about percentage, which is still commonly used in THD, if it's 0.002 or 0.0002, it's a bit awkward to say all these zeros, while we could just say that, okay, it's minus 95 dB or minus 115 dB. So every time the decimal point goes one step, it's at a 20 dB difference. 20 dB means something changes by 10x. And then we have THD plus N. We'll go to THD and THD plus N in another video, but it basically takes this fundamental and compares it to the rest, what is here. Synod is another way of saying THD plus N. Now you may be asking why we don't see the distortion components and the noise in the time domain sine wave. But it's good to remember what these dB numbers mean. Minus 120 dB is 1 million times smaller. So the distortion components are 1 million times smaller than the fundamental. So there's no way you can see it in the time domain sine wave. How do we get this FFD then? We have this time domain representation here. Let's just zoom out. So this is the capture the software is taking. It's around 1 second of this signal. It captures this block of signal, and then it does the fast Fourier transform calculation and creates this plot here. One important feature of FFD is how long it is, the length of the FFD. And here we see now that it's 32K. This signal is sampled at 48 kilohertz. So it means that to get these 32,000 samples, it takes almost 1 second of this signal. And that's why we also see that the FFD updates around once per second, because it always needs to capture at 1 second and then calculate the FFD. This software actually complicates a bit more because we have the capture length and the FFD window are separate settings. So if I change the window so that the capture rate is still the same, because I need to change this separately here. So, but we can see that if we make the window shorter, the FFD updates a bit faster. And then if we make it really long, the update rate is slower. And then we get to see the other features of the window length. So this window is an important concept in FFD because it tells about your frequency resolution. If we use this now, the 32,000 window length, this is what we see. And let's put 4,000. Everything becomes a bit wider, so it's not as accurate when you get lower in the resolution. And then the noise floor also goes up. So if you have something here, the tones are close to one another and you have very poor resolution, you won't be able to tell them apart anymore. So you need to select certain window length for that. Like saying this is a bit complicated in this software. I also don't know how to use it properly yet. If there's a way to put these together, but usually the FFT length and the acquisition length are one same thing, and so you don't need to change this separately. Another important concept is the window function. It's a complex topic and I'm also not an expert in it, but here I'm just gonna show what it does, what it means. So as we said about the acquisition already, the FFT is calculated for a fixed block of signal. So here it's 30,000 samples now, around 0.6 seconds. And the fundamental feature of FFT or any Fourier transform is that it assumes that the signal is periodical. I hear you say it's a sine wave, it is periodical, but when you cut it, it's only periodical if the end point is exactly the same as the starting point. So except some special use cases, the signal is never periodical when you cut it, and that causes some issues in the FFT calculation. This is using a rectangle window, which basically means no window function, and this is how it looks like. We need to use a window function to make it more usable representation, and this software has a huge number of different window functions. Of course, most of them are very, very similar, but some common names, for example, are Han, Hamming, Blackman, Blackman-Harris, and I think here the default is the Kaiser 6. What the window function matters, it's how wide are the tones here, so-called main lobe, how low are the side lobes, what's your frequency resolution, and it also the amplitude changes a little bit. That's actually one of the reasons I'm having -1 dBFS signal, but in most of the windows, like what I had here before, the signal it's lower than -1, because that's also effect of the window function. If you put the rectangle window, then I think it's there kind of -1. Again, now with this rectangle window, if you look at the THD and all these numbers, they're just very awful because the signal looks awful here. It cannot calculate this. And then we start applying different type of windows and we get something out of here. But for example, here we still have this quite wide. The signals have, the windows have different characteristics. And basically you need to select the window based on what do you want to know about the signal. Is it important to know the exact amplitude? Do you want as good separation as possible between adjacent signals here? How much you want to push down these side lobes? And obviously you cannot have everything in one go. So you need to find a compromise what provides a good result. Luckily, when we do this kind of audio measurements, I think our needs are fairly basic in a way. Okay, we wanna push the noise floor down, but we're not usually, our tones are not very close to one another. The harmonics are quite widely apart. Okay, if you do some modulation measurements, then your tones may be close to one another and you need to take that into account. FFT really is the most useful representation of any signal because it tells us so much in just one view. You cannot see distortion from the time domain unless it's very, very bad, because sine wave looks like sine wave. If you can see the distortion in sine wave, you already have like 10% distortion. One way to think about FFT is that it's a bank of very narrow bandpass filters. If you have an FFT length of, okay, let's put something smaller here, 1024. What you can imagine happens here is that your bandwidth of 24 kilohertz in this case is divided into 1000 bandpass filters of equal width. So 48 kilohertz divided by 1000, it shows it here. Your resolution is 47 hertz, and that's the 48,000 divided by 1024. So then you effectively have this bank of bandpass filters that shows you what's in each filter. And when you start increasing the FFT length, the bandpass filters gets narrower, your resolution goes higher. That's one very important concept also in FFTs, that if you look at these tones, the fundamental and the distortion components, and when you change the window length, they are kind of remaining the same height, so the amplitude remains constant for those. But the noise floor goes down when you go to longer window and narrower your bandpass filters or resolution. And that's because the noise amplitude depends on its bandwidth. You always need to look noise within a limited bandwidth. When your bandwidth goes smaller, your noise gets smaller as well. And that's one way to dig out these distortion components in the signal. That, okay, let's see, we don't see the sixth harmonic now. It's under the noise. Okay, what happens if we take very long signal, a lot longer than that. So we have 500,000. Now it's going to take like 10 seconds to do one acquisition. And our frequency resolution is 0.1 Hertz. And now we see the sixth harmonic here and a lot of other crap as well. That is one way to go deep in the noise floor to find what is there. If you don't see a distortion components, by just changing the settings, you will see more of them. Now, after this, it's easy to say that you cannot say what's the noise floor when you look at the FFT. The noise floor is not minus 160 dB here, because when I just change the FFT length, the noise floor changes as well. And of course the noise in the signal is the same all the time. So that's why you can see a lot of things from the FFT, but noise is not one of them. Another way to push the noise down is to use averaging. So basically you just do the same acquisition, the same length, and just add on top of one another, because noise then gets pushed down because it doesn't correlate perfectly. So if you want to measure noise, you need to turn the signal off and just measure the level, the RMS level. But basically this minus 116 here is the noise floor now. And even if you cannot say the noise level from the FFT, one very useful thing is that you can see the shape of the noise floor. Okay, this is flat here, but sometimes it may get higher in the low frequencies or higher in the high frequencies. Although we won't go into details of Fourier theorem here, just to mention that I assume that you know that any periodical signal can be represented as a composition of tones. So if you look at the square wave, for example, here we see 1 kHz square wave. There's the fundamental, and as we know, there's the odd harmonics, which is the decomposition of a square wave signal. Or we can do a multi-tone signal here, 3 tones in 1, 2, and 5 kHz tones. And if you look at the time domain signal, it looks a bit odd, like, okay, what is this? You can tell that there are like some different tones there, but then yeah, it's a bit of a mess, and it becomes even more mess when you have more signals in. But when you see the frequency domain representation, it's very obvious what is there. Okay, you have 1, 2, and 5 kHz. And that's all for now. As this was the first time I did this type of video, please leave some feedback below. What was good, what was not so great, what should I do differently next time. The next videos will be something else, but I will continue this understanding audio measurements in a few weeks' time. Bye now.